This is the energy of light. It's in your book in chapter 5.3. We're going to talk a little bit about the properties of light and of waves. We're also going to talk about how that relates to the Bohr model, and then we're going to do some calculations having to do with frequency and wavelength and light and energy transitions in the Bohr model. So Bohr's atomic model that he came up with for the atom came from our study of light, and scientists had discovered that light acts as both a particle. So if you think of a particle, think of like shooting BBs through a BB gun. Those are particles, but that light also acts as a wave. And a wave, you can think of a wave in a water, has very periodic properties. And that light acts as both a particle and a wave, which is very interesting. And this actually gets a little more into the electron cloud model that Schrödinger and Heisenberg came up with in the 1920s, but also applies to Bohr's atomic model. And we're going to show what that was. Now, if you remember, Bohr's atomic model is that the electrons orbit at specific energy levels at certain distances from the nucleus, not at just anywhere outside the nucleus, which is what Rutherford had said. So first of all, just to review waves, and this should be something that most of you know. You can see we have these two waves here, and waves have certain measurements. One is their amplitude, and amplitude is the distance from the middle of the wave, or what we would call the rest position, to either the crest, which is the top of the wave, or the trough, which is the bottom of the wave. Trough spelled T-R-O-U-G-H, for those of you who aren't clear on that. And then the wavelength, which is the distance from one crest to another crest, or one trough to another trough. And then we have what's called the frequency of a wave. So the frequency is the number of wave cycles, or full wavelengths, to pass by a certain point per second. So high frequency has a lot of wavelengths passing by a certain point per second. A low frequency has just a few wavelengths, or fewer wavelengths, passing by a certain point per second. And frequency is measured in the unit of hertz. We'll talk about that a little more. Or, slightly awkwardly, seconds to the minus 1, or 1 over seconds. Just to be clear though, frequency should not be confused with speed. You can have a low frequency wave traveling pretty quickly. You could have a high frequency wave traveling pretty slowly. So think of frequency almost as how bunched together the crests are. That would be a qualitative way of saying it versus a quantitative way. And that could be moving quickly or slowly, but the wavelengths are bunched together, the crests are bunched together. Or they could be moving at the same speed. So I'll show you how that works in a moment. So this is a review of the electromagnetic spectrum. Hopefully you've seen this before, but there's a couple things I want to point out. On the high frequency, high energy side, so if we get our pen here, so this is high frequency, high energy. That's also the shorter wavelengths. Okay, these numbers up here are wavelengths. You can see their distances. 10 to the negative 12th meters, 10 to the negative 9th meters, which is 1 nanometer. All the way over here, long wavelengths, 1 kilometer, or 10 to the 3rd meters. And then over here we have low frequency, low energy waves. So long wavelengths on the electromagnetic spectrum have low frequency and low energy. Short wavelengths over here have high frequency and high energy. And then in the middle, kind of right here, and this is expanded down here so that you can see it, is the visible spectrum. So the longest wavelength is red, then orange, yellow, green, blue, indigo, and violet. And that's what we can see, and you can see down here the specific nanometers or wavelengths associated with each color. Again, this should be somewhat reviewed to you. I assume you are familiar with the electromagnetic spectrum. Okay, so here are some equations that then deal with light. So one of the things, and if I go back for a second, let's see, is that some of you know on the electromagnetic spectrum that all of these wavelengths travel at the same speed. What speed is that? It's the speed of light. So this is where we're talking about simply because something's high frequency doesn't mean it's traveling faster than something that's low frequency. These all travel at the speed of light. So going back to these equations, if you look at what's sort of the second equation down here, is the speed of light, which is represented by the lowercase letter c, and that's 3.00 times 10 to the 8th meters per second, equals this Greek letter lambda here, which is lambda stands for wavelength, and that's measured in either nanometers or meters, times the Greek letter nu, which is the symbol for frequency, which is 1 over seconds or hertz. Now, you'll often hear me say in class, instead of saying nu, I say V, which isn't correct, but it's always how I've remembered it. So if I say that, feel free to raise your hand and say, wait, don't you mean nu? Because I do. It is the Greek letter nu, not V. One thing about wavelength measured in nanometers or meters, oftentimes we'll talk about nanometers when it doesn't make sense to use meters because the numbers would be too small. But if you're using the speed of light in meters per second, you have to have your wavelength in meters. Otherwise, your units aren't going to correspond. So keep that in mind. If you have a question in nanometers, you're either going to need to convert it to meters or convert the speed of light to nanometers. And then the second equation up here is, and this is where a lot of times I'll say E equals hV. In fact, it's E equals h nu. E is energy measured in joules. Nu is the frequency, which is 1 over seconds or hertz. And then we have this thing h. H is a constant. It's a constant called Planck's constant. A scientist whose last name was Planck came up with it. And Planck's constant is 6.63 times 10 to the negative 34th joules per second, or I'm sorry, joules times seconds. So you can see how that would work to cancel out joules times seconds multiplied by 1 over seconds. Your seconds are going to cancel and you're simply left with joules. Similarly, meters over here times 1 over seconds is going to give you meters per second, or speed of light. So let's look at how we can manipulate these equations. So from the two equations I gave you, the speed of light equals lambda nu and energy equals h nu, we can rearrange these equations and come up with one equation altogether. So we can rearrange the first equation to solve for nu, in which case we get nu equals the speed of light divided by the wavelength, or frequency equals the speed of light divided by the wavelength. And then we can substitute in, let me get our pen back up here, we can substitute in the speed of length divided by wavelength for the frequency here. And if we do that, let's get rid of that, we end up with energy equals Planck's constant times the speed of light divided by the wavelength of the wave. And so that's a way to relate all of those together. Take a second and just let that sink in. Okay, so what was Bohr doing and how does this all relate to the atom? So I want to show you some things that you might know. So this is the spectrum of sunlight. It's not actually sunlight, but it would be the spectrum of, say, a light bulb, white light. White light gives you this continuous spectrum that looks like a rainbow. It, in fact, is the rainbow. That's why we see a rainbow. When sun shines through a raindrop, we get this beautiful rainbow, continuous spectrum. However, some of you who took physical science know that elements don't give off white light. So this is hydrogen light. So it's hydrogen gas being electrified, and we're going to see some of these in class, and they give off purple light. Hydrogen gives off this kind of purplish pink light. Where a lot of you've seen this in physical science is if you remember back to the flame test, and you remember burning different elements in a Bunsen burner and seeing that different elements change the Bunsen burner flame a certain color? That's what this essentially is, except it's in like a tube. So this is how neon lights are made, except those are made out of neon, or if they're other colors, other colors. So if you see a neon light that's giving off a purplish pink, that may be hydrogen. What's interesting is, if you take a prism and hold it up to the hydrogen spectrum, instead of seeing this continuous spectrum that we see with the sunlight, like the rainbow, we see this. We only see certain parts of that continuous spectrum. We can see that they happen kind of where they are on the continuous spectrum. So we have a red line here, and then a large space where there's nothing, and then a blue line, and then a large space, and then a violet line. So that's a spectral signature, a spectral fingerprint of hydrogen. And each element has its own unique spectrum, like a fingerprint. So you could use a spectroscope or a prism. Spectroscope's like a fancy prism. I'll show you one in class. To figure out what element you have based on those spectral lines. So, okay, how does this now relate to the atom? So, Bohr was working with hydrogen, and he had all this kind of knowledge that he pieced together. And he realized that electrons absorb energy as they move to higher energy levels. So you can see on this diagram down here, right down here, this electron is moving to a higher energy level, so it must absorb energy. Then he realized, so electrons must release energy as they move to lower energy levels. I don't know if this was exactly Bohr who realized this, but Bohr is credited with putting this all together into the atomic model. You'll notice on the side here we've got our principal energy levels, N1, N2, N3, N4, N5, and so forth. And one of the things you might notice is that as you go from N1 to N5, the energy levels actually get closer together. Those of you who read about this in the book know that. Those of you who didn't, that might be new to you. So what Bohr realized was that you could calculate the wavelength of the light emitted, because we would know the wavelength, so we could figure out the wavelength emitted based on the energy transition. In other words, you can figure out how much energy is given off here based on the wavelength that you're seeing. What this meant was that specific spectral lines, those spectral lines we just saw for hydrogen, must correspond to specific energy levels. Violet, a line of violet must correspond to a certain change in energy level of an electron. Red must correspond to a certain energy level change, which meant that these electrons had to be at specific distances from the nucleus, not at random distances from the nucleus, which is how Bohr got his model. Okay, so just to make things a little more mathematic for those of you who like to see where all this is going, there was this scientist dude named Ryberg, and Ryberg created an equation that actually allowed for the wavelength of light to be determined for different changes in energy level. So this is his equation here. 1 over lambda, or 1 over wavelength, equals the Ryberg constant. R sub h is the Ryberg constant. It's 1.097 times 10 to the 7th 1 over meters, multiplied by 1 over n sub f squared, where n sub f is the final energy level, minus 1 over n sub I squared, where that's the initial energy level. I know that's a lot to take in, but let's do some examples so that you can see how this all relates. Okay, here are some examples, and I highly recommend you trying to do the example before you look at the answer. Find the frequency of light with a wavelength of 746 nanometers. So pause the video, try to do that. You have 3 equations that you've been given. Figure out which one you're going to use and how to calculate that, and then start the video again. So the first thing you should realize you need to do is convert nanometers to meters. So that's done by multiplying 745 nanometers times 1 meter over 10 to the 9th nanometers, which gives us 7.45 times 10 to the negative 7th meters. Now that I have my wavelength in meters, I can use this equation where I've rearranged the C equals wavelength times frequency to get frequency equals speed of light over wavelength. So my speed of light is 3.00 times 10 to the 8th meters per second over 7.45 times 10 to the negative 7th meters. That comes from up here. Equals 4.03 times 10 to the 14th hertz, or 1 over seconds, whichever you prefer. Find the color of light now with the frequency 6.45 times 10 to the 14th hertz. So in order to do this, we're going to need to know the wavelength. So we need to change frequency to wavelength. So in this case, we can use the equation lambda equals C over frequency, which is again simply rearranging the above equation. And so here we get the speed of light divided by 6.45 times 10 to the 14th, 1 over seconds. I changed hertz to 1 over seconds so you can see where the meters come from, because then our seconds will cancel out. And this gives us 4.65 times 10 to the negative 7th meters. When we're talking about color, we're talking about the visible spectrum, which we talk about in nanometers. So if you convert that, that then gives you 465 nanometers. If you go back to the slide, or in fact in your book, look at the visible spectrum, you'll see that 465 nanometers corresponds to blue light. All right, now for the big one. What wavelength of light is produced with a change in energy level from N3 to N2? So obviously you're going to need your Ryberg equation. So go ahead and solve that. So here is the Ryberg equation. So first I've got my Ryberg constant, 1.097 times 10 to the 7th 1 over meters, times 1 over 2 squared. The 2 comes from here. That's my final energy level. Minus 1 over 3 squared. That's my initial energy level. Remember, light is produced when electrons go from higher orbits to lower orbits. So that second n is always going to be greater than your first n in the equation, because it's falling down from a higher level to a lower level. And that gives you 1.52 times 10 to the 6th 1 over meters. This doesn't give me a wavelength. This gives me 1 over wavelength. So I need to take the reciprocal of this number. So the second part of this would be wavelength equals 1 over 1.52 times 10 to the 6th 1 over meters, which gives me 6.56 times 10 to the negative 7 meters, which I could convert to nanometers. So what color of light is given off from the above change? So we know that it's 6.56 times 10 to the negative 7 meters. All we need to do here is convert that to nanometers. We get 656 nanometers, which corresponds to red light. I know that's a lot to take in. Please look over 5.3 in your book. Come prepared tomorrow to ask questions and answer some questions. Also, feel free to put any comments you want onto the comment section of the YouTube.